Hey, it's Mr. K doing a video for AP Physics 1 and C Mechanics. This is going to be pertinent to both. We're going to get into a little bit of calculus, but really not that much. It's still going to be very much applicable to both classes. So here we have a velocity time graph before you, and there is nothing on it. Let's go ahead and make something up. Let's say we have a velocity of 4 for that long, and then we go down to nothing. And we keep on going down, and then let's say we have something like that. That's fun. So here is a velocity time graph. Our main focus is going to be on the very first part. We're going to go more conceptual for the second part, but there is definitely a point to it. So here we go. The very first part, we need to figure out what's going on with our object. Let's say this object is some random object out there, and it is we have a graph that describes its motion in the horizontal, because we would need another graph to describe its motion in the vertical. So we can only pick one. So here we are. What's going on? Okay. Pause it. Figure out what's going on. 3, 2, 1. Unpause. And if you didn't pause, then here we go. So we have an object. It is moving. It is moving at a rate of 4 meters per second. Constantly for 4 squares here, so we'll call that 4 seconds. And then at the 4-second mark, it starts to reduce its velocity down to 0, but then it continues to change its velocity until the 8-second mark. So let's say this is 4, 6, and 8. And then it starts to do something wonky over here, and we're not going to talk about that just yet. Let's focus on the first part. So, very first part, we have an object. It's moving at a constant rate. Average velocity is its velocity. So 4 meters per second for 4 seconds. How far did you go? Well, 4 meters per second for 4 seconds. You went 16 meters. That also happens to be the area of this first initial square. All right, so you find the area of a rectangle or a square here. For the units, we have meters per second on this side, we have seconds on this side, and so we have the total units of meters per second times seconds. That's meters. Area gives you how far you went, the displacement for that section. The acceleration, which would be the ratio of the change in velocity over the change in time, well, that's nothing because it didn't change velocity. And that's pretty much all we can do for that first part. So slope there is 0 acceleration. This is a velocity time graph. Area there, it's 16. You went somewhere, you went 16 meters forward. For the next part, let's look at those exact same things. The slope, we have a change of 1, 2, 3, 4 negative. We have a change of velocity of -4 over a change of time of 2 seconds. And so we're talking about a -2 change of meters per second every second, and so that is a -2 acceleration. So this is your acceleration. It's -2 for that section. It continues on from 6 to 8 seconds. -2 meters per second, meters per second squared. All right, let's look at the area. The area of this thing, it's a triangle. It's 1/2 base times height. Take the area of a rectangle, cut it in half. So we have a base of 2. We have a height of 4. 2 times 4 is 8. Cut that in half, you get 4. So 4 meters there, displacement. And then you have an identical triangle, which is going to give us 4 meters here, but negative displacement. So we go back the other way. Essentially, from 4 to 8 seconds, you've moved forward, but then you've also moved backward. You've slowed down in that time. You've sped up in the other, you sped up backwards because you're still accelerating at the same rate, and you cancel out your motion. Now, that's great. What happens next? Okay, and this is where it gets a little bit tricky. We have a velocity that is still continuing to increase, and yet at this point, it starts to decrease again. So here, it's like we have an acceleration of 2 meters per second squared, but then here we have an acceleration of 0 meters per second squared, because remember, the acceleration is the slope of this graph. So our acceleration seems to be changing here. it starts to be, well, negative 2 meters. It starts to be, well, changing in the positive way. So we have a curvy kind of, we have a little bit of a whoop there, and it's a upward facing inflection, and so we have a positive change of that velocity, or that acceleration. As opposed to over here, where we have this velocity that is increasing, so positive acceleration again, but then here we have this 0 meters per second squared. This 0 slope there. Remember, the slope on this graph is the acceleration. So we go from a positive slope to 0, and we have this inverted inflection, and so we have this changing acceleration that is now reducing, getting back more towards 0, and then getting negative and negative and more negative. All right? So if we wanted to talk about the velocity here, we need to talk about two different kinds of velocity. One is your average velocity, and that's probably going to be your most useful. So we have something called the average. And how do you find the average? Well, you take all the values that you can, and as long as they're equally spaced apart or equally weighted, and then you add those together, and then you divide by however many you added together. So if you want to find out your average, your grade average, you take, let's say your grade is only based on test grades. You take all your test grades, you add them up, and then you divide by the number of tests that you have, and that's your average. If you wanted to find your average speed, let's say, you would find how far you went, the total distance, and then divide that by the total time that it took. Now, that doesn't mean that you couldn't have been going faster or slower, but on average, if you know how far you went distance-wise, you can divide that by time and find your average speed. Same for your average velocity. Find your displacement. Divide that by your time. Your instantaneous speed or velocities could be different, but that brings us to this point. So average versus this other thing called instantaneous. So if we look, for the first part, our average speed is 4 meters per second. For this second part here, our average speed between 4 and 0 is 2 meters per second. For this third part, our average speed or average velocity is going to be negative 2 meters per second. What about here? Okay, and that's going to be a little bit different. It looks like we have an average value of somewhere in the middle between all here. But could we talk about instantaneous compared to average? Instantaneously, at 2 seconds, my speed is my average speed. My average velocity is my instantaneous velocity. At this point here, at 4 seconds, my average is still my instantaneous velocity. But when I start to go down here in this section, for this section, if I wanted to talk about the time of 5 seconds, my speed is 2 meters per second. Does that match the average speed from the very beginning? And we'd have to say no. Well, from the beginning, we've been moving the majority of 4 meters per second. The average here would be closer to 4. But there's a difference. Instantaneously, that velocity is 2. Now, if we wanted to talk about the average velocity for this particular section, instantaneously and average would be the same at that 5 second mark. Now, over here, if we talked about this section, my average would be somewhere in the middle. But instantaneously, it could be any one of these. All right? And so here's where it really starts to matter. For the instant, we could look at the instantaneous, let's say the instantaneous acceleration, which would be the slope of this line. The instantaneous acceleration of this line right here would be whatever this rise over run would be there, whatever that is. Okay? But the average acceleration would depend upon the change of velocity over some change in time that we're talking about. So if I wanted to discuss with you, and we wanted to make a point of the time between here and there are, when our accelerations are 0, in between here, do we have a change of velocity? Well, we'd have to argue, yeah. We go from a negative velocity to a positive velocity, so we have a change in velocity. Do we have a change in time that occurs? And we'd have to say, yeah, we do. We do have a change in time that occurs. If you found the change in velocity over that change in time, this would give you some acceleration value, but it would give you the average acceleration value for that time interval. If you wanted to find the instantaneous acceleration for that time interval, you would have to bring these 2 points closer and closer and closer together. So, if we looked at this point and this point, and we drew that line, that would represent and have that slope of whatever average acceleration value we have, we would see instantly at this moment that this slope of this red line that I just drew is not the same slope as the point in the middle, which we denoted before. How would you find the slope of the point right in the middle? Because it's a little bit steeper, isn't it? Well, you would take your ruler, if we did this visually, and we would try to find that one point that represents that special piece. And so this new line there, that would have the same slope as that particular point that we talked about. That has a name. It's a tangent line. All right? And so essentially what we've done is we've moved these 2 points closer and closer and closer together. And when we do that, we start to get more and more and more to a value that is the same value as the slope of that line. And so when we move those 2 points super, super, super close together, you can draw a line that connects those 2 points, and that would be the same slope as that particular point itself. And that is the instantaneous value for that acceleration. You can do the same thing for velocity, if the slope was the velocity on a position time graph. But as you bring those 2 things closer and closer and closer together, this delta starts to become something a little bit different, because delta, the triangle is kind of like a big change. And as we get smaller and smaller and smaller and smaller, we start to have a smaller and smaller and smaller change. And so we're going to lowercase that, and we get what is called a differential. Right? And this lowercase d represents, well, let me write this first. This lowercase d represents the smallest change of the smallest change, but the ratio of those changes is still going to be the same for that instant. I guess that's not the best way to put it, but as you get smaller and smaller in your changes, you get the differential. So we have a dv, which is a super small change in velocity, over a dt, which is a super small change in time, and that ratio should match the slope of that point. And we're going to be able to work with that a lot. That's going to be very useful in calculus. That's going to be extremely useful whenever we start to do the upper level math, the calculus. And then we'll start to move stuff around as well. We'll go into the methods of calculus and how to do all that, the power rule, the quotient rule, the product rule, chain rule, and all that. Talk about Newton and how he came up with all this during a pandemic. Imagine that. All right. Next video is coming up. We will stop this one here.